Hello everyone, this is Siddharth from Samsung Research and Development Institute, Bangalore. Today I will be presenting our work on media restoration using Volterra networks, which was done in collaboration with my colleagues Amit and Loy. The objective of this work was to develop media restoration approaches to improve image and video quality. Image and video quality is usually affected by degradations which occur during the process of capturing, saving, sharing, or editing. It is crucial to restore such degraded images in order to prevent loss of information and ensure best visual experience for users. In this work, we will be targeting mainly two kinds of degradations. The first one is motion blur during capture, which occurs due to camera motion during the process of capturing images or videos. And the objective will be to achieve a blurred image. Similarly, we will also look at sensor noise that is introduced during capture, and the objective will be to achieve a denoised image. In order to achieve this, we introduce a novel class of media restoration networks inspired by the Volterra series formulation. The advantage of using a Volterra series formulation is that it allows for incorporation of nonlinearity into the network architecture via higher order combinations. As depicted here, Volterra filter is a nonlinear learnable filter which establishes a relationship between the input xt and the output yt, driven by an error metric which is depicted by E being equals to. A kth order Volterra filter can be described as such, where the first term represents a linear convolution between the main matrix W1 and the input xt. This is the same as a convolutional layer in the traditional CNNs. But instead of using activation functions to introduce nonlinearity, we will use second order or higher order convolutions to achieve that. So the second term in this equation shows a second order convolution between W2 and the input xt. And similarly, the last term is a kth order convolution between the weight matrix WK and the input xt. However, due to certain limitations of a Volterra filter as described in the previous slide, it is not easy to implement for complex tasks which require high nonlinearity. The first limitation is that the complexity of a Volterra filter increases exponentially with desired order of nonlinearity. And a Volterra filter of order k and filter length L requires solving L raised to k equations and its parameters by sum over L raised to k parameters. Similarly, for a 2D Volterra filter with the convolutional kernel of 2 times t, the required number of parameters becomes sum over e raised to k. Furthermore, higher order convolutions are not supported by commonly used deep learning libraries such as TensorFlow and PyTorch. So, what is the solution? We propose cascading of second order Volterra filters to generate high nonlinearity without incurring the same complexity. As depicted in this figure, the input X is first fed to a Volterra layer which realizes a second order Volterra filter to get the output X1, which is again sent to another Volterra layer which is another second order Volterra filter, and so on and so forth. So for 3D Volterra filters, which will be used to process videos, we will be looking at three-dimensional filter with two spatial dimensions and a time dimension. And for 2D Volterra filters, we'll be looking at only the spatial dimensions, and the formulation will be as shown. The advantage of cascading the Volterra layers, as discussed in the previous slide, is that we can achieve a very high non-linearity without requiring too many Volterra layers, and at the same time, we can reduce the number of convolutions required as well as the number of parameters required as compared to the previous formulation. In spite of the cascading trick that was discussed earlier, implementing a VNN can be computationally costly. This cost is majorly linked with the second order kernel. So we propose lossless and lossy approximation techniques to alleviate this problem. In the lossless approximation, we rewrite the VNN formulation as shown here, utilizing a circularly shifted map of the input xc minus 1 in order to realize the second order. The second order kernel in this equation requires p squared linear convolutions to implement. However, on discarding the redundant terms in the above equation, we can reduce the number of required linear convolutions to PC2 instead of p squared. Another way of approximating the second order kernel is to use a low rank approximation. This can be achieved by decomposing the second order kernel into separable linear convolutions, and this leads to further reduction in complexity as well as the number of parameters. However, it also causes some loss of information and hence the term lossy. The Volterra filter can also be considered as a generalized activation function. Volterra filter is capable of providing an approximation to any continuous function, which includes the standard activation functions such as range, sigmoid, or tan. While traditional activation functions are fixed, the Volterra filter formulation actually learns a data-driven activation or nonlinear. As shown in this figure, the Volterra filter can actually approximate value or tan H, and hence it is considered as a generalized activation. To assess the efficacy of the proposed approach, we conduct experiments targeting prevalent degradations in images and videos such as motion blur and camera sensor noise. We develop a network architecture inspired by the MR-VNet, and each encoder and decoder block is made up of Volterra layers instead of the traditional convolutional layers. We evaluate this module for image deblurring and denoising on GoPro as well as SID datasets. As can be seen from the results, our proposed approach actually outperforms the SOTA methods while requiring lower computational complexity. We further validate our approach for videos by evaluating on the CRVD dataset for video denoising. Here we see that the model is able to achieve flicker denoised videos while outperforming SOTA techniques in terms of PSNR as well as SSL. In conclusion, we presented a novel class of restoration architectures inspired by the Volterra series formulation. We also introduced two architectural variants to make Volterra filter realizable for deep learning tasks. Furthermore, we show that none of the traditional functions actually appear to contribute additional nonlinearity beyond what the Volterra filter already learns, indicating that the VNN is actually capable of learning required nonlinearity from the data itself. Finally, experimental evaluations were conducted on diverse datasets, including GoPro, REDS, SIDD, and CRVD, to showcase the versatility of the proposed architecture. Thank you everyone for taking out the time to watch this video. And if you have any questions regarding this work, you can feel free to contact me at the provided email.